So we're back to talking about rational functions again, and since it's been a little while since we've looked at rational functions, let's start with just a bit of a review. So in this first example, we're going to look at three different functions, and we are going to determine the asymptotes of the function and the end behavior as well, and we're going to talk about how those things are actually related. In our first example, we have f of x equals x divided by x squared minus 1. Now, when you're wanting to determine asymptotes of rational functions, you always start by looking in the denominator and kind of asking yourself, can the denominator be equal to 0? In this case, I can see that x equals 1 or negative 1 is going to give us a denominator of 0. So x equals 1 or negative 1 can't be in the domain of this function since you can't divide by 0. Now, if you're having difficulty seeing that, a good idea is to factor the denominator here. When I factor the denominator, I get x divided by x minus 1, x plus 1. So that actually tells us that there are vertical asymptotes at x equals 1 and x equals negative 1. So those vertical asymptotes, x equals 1 and x equals negative 1. Now, the only time those would be wholes instead of vertical asymptotes is if you had something like this. So imagine you had a function like this right here, and you had x plus 1 divided by x plus 1, in which case these would divide out. That case, that would mean that x equals negative 1 is a whole. Okay, since you still can't sub in x equals negative 1 into this equation, because you divide by 0, but nothing strange happens as numbers get close to negative 1 because these numbers just end up dividing out. So this would be the case when you have a whole. Now that's not what we have in this example. In this example, we have the x minus 1, the x plus 1. They don't divide out. As x gets closer to 1 or negative 1, this thing blows up to infinity, which creates a vertical asymptote. Next, let's talk about end behavior of the function and also any possible horizontal asymptotes, because end behavior and horizontal asymptotes are really closely related. Finding horizontal asymptotes is actually basically the same as determining end behavior. Now remember that determining end behavior is determining what happens as x gets very, very large, either very large in the positive direction or very large in the negative direction. Another way of saying that is to say determine the limit as x approaches positive or negative infinity of x divided by x squared minus 1. Now, how do we do that? Well, in class, we've discussed a number of ways that you can determine this limit or this end behavior. One option was to begin subbing in large values of x. Now, there's no specific rule about how large the values of x need to be, so you should try a few. Since there's no large numbers in the equation, odds are the large values of x don't need to be that big. If you subbed in x equals 10,000 and then subbed in x equals 100,000, you'd probably see the end behavior as x approaches positive infinity. And then for negative infinity, you could use negative 10,000 and then negative 100,000. And I think you'd convince yourself what the end behavior of this looks like. So that's one option. Just sub in large numbers. Another option, and if you did that, by the way, you would notice that you end up getting closer and closer to 0. Now, another option to realize that this is 0 is to just actually look at the degree of the numerator and the denominator. Since the degree of the numerator is less than the degree of the denominator gets big a lot faster than the numerator. And of course, fractions with large denominators start to approach 0. Okay, think about like 1 over 9,999. That's a very small number. We think about that kind of as talking about like the dominant term. X squared is the dominant term here, and since it's in the denominator, it tends to make the whole fraction go to 0. Now, there was an algebraic way that we could show that as well. Now, you don't have to do this, but one thing you can do is you can divide the top and bottom of the fraction by the dominant term. In this case, divide everything by x squared. Let's see what that looks like. When we divide everything by x squared, we divide x by x squared to get 1 over x. We divide x squared by x squared to get 1, and we divide negative 1 by x squared to get negative 1 over x squared. So these two fractions are actually equivalent. Like this is a legal algebraic move, although it is a very strange one to do. It helps with limits because now we can imagine what happens as x gets really, really big. Well, as x gets really, really big, 1 over x becomes 1 over a big number, which gets closer and closer to 0. Okay, 1 stays as 1, but this also becomes a very small number as x becomes big. So we end up getting a fraction, like I think of this as being like 0 over 1. So the top approaches 0, the bottom gets closer and closer to 1. Well, that's equal to 0, and so we can see that this answer is in fact equal to 0 by dividing. So really, I've given you sort of 3 different options here. Using a big number to determine end behavior, using the fact that the numerator has a larger degree than the denominator, or dividing everything by x squared. All should give you an answer equal to 0. Now we can be a little bit more specific. Sometimes when something's approaching 0, by the way, sorry, let me stop for a second here. One thing we can determine right now is because the answer was 0, that means we have a horizontal asymptote at y equals 0. So we can determine that right now. We can also be more specific about our end behavior. So does the graph get closer and closer to 0 from above or from below? And what we need to do now is we actually need to break this limit up and realize that answer is going to depend on whether x approaches positive infinity or whether it approaches negative infinity. So the limit as x approaches positive infinity of x over x squared minus 1, we already know that that limit is equal to 0. But let's just talk about a little bit more specific. So 0, if you're getting close to 0, that means you're either a very small positive number or a very small negative number. Let's look at x approaches positive infinity. This is a positive number, so the numerator is positive. X squared is a positive number, and as x gets big, when you subtract 1, you will still get a positive number because this is obviously bigger than 1. Okay, it's gigantic. It's infinity squared. So a positive divided by a positive is a positive number. So although this is approaching 0, it will always be a positive number. So that little symbol there means 0 from above, or 0 plus a little bit. Now how about the limit as x approaches negative infinity? Again, we do already know that that is 0. But in this case, the numerator is going to be a negative number. The denominator is going to be a negative number squared, which is a positive number. Subtract 1, which is positive. So here we have a negative divided by a positive, which is a negative number. And so that is 0 from below, or 0 take away a little bit is the symbol we use there. So we have taken our end behavior. Although all the work up here let us know that we have a horizontal asymptote at y equals 0, we know that as x approaches positive infinity, it's 0 from above. And as x approaches negative infinity, it's 0 from below. And that can help us if our goal is to sketch the function, because we know there's a horizontal asymptote at y equals 0, and we know which direction the graph approaches that asymptote from. In the positive x direction, it's going to be above it, and in the negative x direction, it's going to be below it. Let's actually take a look at the graph in Desmos and make sure that it does in fact show these things that we've said, the end behavior analysis, as well as our vertical asymptotes. Okay, so I'll type that equation into Desmos. Y equals x divided by x squared, take away 1. Okay, so it does take a bit of work here, but you can see there is in fact a vertical asymptote at x equals 1 and x equals negative 1. If you want, you can actually graph that in Desmos as well. X equals 1 and x equals negative 1. I'm going to show those as dotted lines instead, just look a little bit better. And there's our vertical asymptotes. And sure enough, you can see the horizontal asymptote at y equals 0 as well. Okay, and sure enough, the graph approaches y equals 0 from above, and here from below. So I hope you realize that finding end behavior is similar to finding horizontal asymptotes, or in this case, sometimes more generally, end behavior asymptotes. Now, what about the graph in here? Well, 0, 0 is a point on the graph. you would need to take a look at what happens as what happens to the function as it gets closer to -1, and what happens to the function as it gets closer to +1, and in order to determine this part of the graph right here. But that's not really our focus right now. Okay, let's try the next example. Now we have y equals 2x divided by x plus 5. So the easy thing I think to get first is to realize that there is going to be a vertical asymptote at x equals -5. You don't need to factor to see that in this case. It's right there for you. Okay, now the end behavior. So what happens as x approaches positive or negative infinity? Unlike the previous example, the denominator does not have a higher degree than the numerator. So there's no way to tell for sure what's going to happen here just by using that fact like the last example. So one option is to just start subbing big numbers in. Okay, start with x equals 10,000, then maybe x equals 100,000, and then -10,000, -100,000. See what happens. See what that appears to be getting closer and closer to. So that's one option. Another option is to divide the largest term. In this case, the largest term is just x. So if I divide the top and bottom of this fraction by x, let's see what we get. This time I divide by x, I get 2x divided by x is 2, x divided by x is 1, and 5 divided by x is 5x. So again, these are equivalent algebraically, even though this one is strange. But the benefit of this is that I can look and I can say, okay, as x gets really, really big, 2 stays at 2, 1 stays at 1, but 5 divided by a big number will get closer and closer to 0. And that actually gives us the answer, 2 divided by 1, which is equal to 2. And that tells us right away that there must be a horizontal asymptote at y equals 2. Now, you might have realized that the degree of the numerator and the degree of the denominator are the same here. So in general, once you have looked at these enough, you could realize, like, look, the dominant term is 2x and x. Those divide out to give you 2. Or another way of looking at it is, look, this is 2 times a huge number. This is the same huge number plus 5. Well, the bigger x gets, the closer and closer that's going to get to 2, because adding 5 to a big number becomes less and less significant as x gets bigger and bigger. We could also look at this and decide, does it approach, so talking about our asymptote, is it going to approach the asymptote from above or from below? So in order to determine that, I'm going to break up the limits into the positive limit and the negative. Okay, I'm going to think about, I know the answer is 2 in each case. So that part I've already determined. It's just a matter of whether it's 2 from above or from below. So let's start with x approaches positive infinity. Clearly the top is going to be 2 times a big number. Sorry, let me try that again. If the answer were exactly 2, it'd be 2x divided by x. But as it turns out, you've got x plus 5 on the bottom. So in order to make this 2, you'd expect to see 2 over 1, but instead you have a number like a little bit bigger than 1. So this is going to be a number, like if you imagine putting 100 in there for now, you'd have 200 over 105, which is a little smaller than 2. So you're always actually a little bit lower than 2. Notice it's a little more difficult to figure that out than it is when you're dealing with 0, because 0 is nice. It's either, if it's above 0, it's positive. If it's below 0, it's negative. But when it comes to a number like 2, you have to think a little bit harder to do that. If you sub big numbers in to determine this limit, you probably already know this answer anyways. If I go to negative infinity now, in this case, you could imagine a number like 100. You'd have negative 200 over negative 100 plus 5, or negative 200 divided by negative 95, which is positive 2, but it's actually a bit bigger than 2. So it'd be 2 from above. You can just use big numbers if you're not quite understanding how that works. So we determined quite a bit about this graph now. We know that it will have a vertical asymptote at x equals -5, a horizontal asymptote at y equals 2, and it will approach 2 from above in the negative direction on the left side of the graph, and it will approach 2 from below in the positive direction or the right side of the graph. So we'll switch to Desmos now and we'll take a look at this one. So there you see it's all in Desmos, y equals 2x divided by x plus 5, and I've also graphed the vertical asymptote at x equals -5, okay, right here, and our horizontal asymptote at y equals 2. Not a very exciting graph, but sure enough, the end behavior is correct. 2 from above in the negative direction, 2 from below in the positive direction. Okay, for our third example, we have f of x equals x squared minus 4x plus 4 divided by x minus 1. So the first thing I notice is in the first example, the denominator had the larger degree. The second example, the numerator and the denominator had the same degree. And in this example, the numerator has the larger degree. So that's really going to come important when we talk about end behavior. The other thing I'm going to notice right away is there's definitely going to be a vertical asymptote at x equals 1. Okay, vertical asymptote at x equals 1. So now the end behavior, or the limit as x approaches positive or negative infinity. So again, one way to solve this would be to start plugging in very large numbers of x. So starting with 10,000 and maybe 100,000, and then the same thing with negative 10,000, negative 100,000. And seeing what you get. I think if you do that, you'll find you're getting some very large numbers. So when you see those very large numbers, you'd realize that the answer to this is either positive or negative infinity. In fact, as x gets really big in the positive direction, you'll find you get very big positive numbers here. As x gets bigger in the negative direction, you'll find out you get very big negative numbers. So the answer is positive or negative infinity. Now, how could you tell that without using big numbers? Well, you might remember that we discussed this idea that if the numerator has the larger degree, then the top of the fraction is getting very, very large compared to the bottom. And when the top of a fraction gets very, very large compared to the bottom, you get numbers that go to infinity, not to 0. That's another option. You also could do what we did in the other two examples, which is to divide the top and bottom of the fraction by the dominant term, or in this case, x squared. So if you choose to do that, let's just see what that looks like. So dividing everything by x squared divided by x squared gives you 1. 4x divided by x squared gives you 4 over x, and 4 divided by x squared gives you x squared. And then finally, x divided by x squared is 1 over x, and then 1 divided by x squared, just 1 over x squared. Now, the reason we do this is that it's very easy to see what is approaching 0. So 4 divided by a big number approaches 0. 4 divided by a big number squared also approaches 0. Okay, these also approach 0. And again, approaching 0. So then when we look at this, we realize, what are we left with here? We're left with a 1 divided by a number getting closer and closer to 0. So think about 1 dividing by a number closer and closer to 0. So 1 divided by 0.00001, which would be a million. So this answer is infinity. Now, the answer also depends, is it positive infinity or is it negative infinity? Well, that depends on the plus or minus here. So let's start by looking at the positive infinity. Okay, so as x approaches positive infinity, now we know the answer is going to be infinity. We just don't know whether it's negative infinity or positive infinity. Well, we do know if we just start subbing numbers in, but we can look here and see why it is in fact positive infinity. So 1 minus a number getting closer to 0, the top of the fraction is positive. The bottom of the fraction, you have 1 divided by a positive number, which is positive. Subtract another positive. But 1 over x will always be bigger than 1 over x squared. It's like 1 over 10 compared to 1 over 100. And so we end up getting a positive number on the bottom as well. So this is going to be positive infinity. Now how about in the negative direction? So now x is getting closer and closer to negative infinity. The top is still going to be a positive number because it's 1 subtract a very small number. That's positive, no matter whether that small number is negative or positive. Okay, look at the denominator. You've got a negative number, subtract a positive number because 1 over x squared is positive. So the top of this fraction is going to be positive and the bottom is going to be negative. So it's going to be a negative number, negative infinity. Next, let's take a look at the graph of this function. And not only is that going to confirm what we found, it's also going to introduce a new question that we haven't looked at because we have technically looked at all this stuff in class already. Okay, so you can see now that I've typed the equation into Desmos here, as well as the vertical asymptote x equals 1. And so we see the graph approaching x equals 1 here, x equals 1 down here, and the end behavior is confirmed. As x gets really, really large, the y values approach infinity. As x gets really small or big in the negative direction, the y values approach negative infinity, which is exactly what we thought was going to happen. So that's this end behavior right here. That means that this graph also, by the way, does not have a horizontal asymptote, because there's no horizontal line that it approaches. But something about this graph is still a bit strange. Look at the end behavior. it is kind of weird. It looks like a straight line even if I zoom out enough. And it's certainly different. We've seen end behavior that approaches positive and negative infinity. In fact, based on what we did with polynomial functions, there was this polynomial function I've given you right here. Remember that this one has a positive leading coefficient, so it behaves like a line, and technically has the, according to what we've learned, has the exact same end behavior as the rational function. But when I add it to the graph, look at its end behavior. There's no doubt that that's different. It blows up to positive infinity and it blows up down to negative infinity, but not only much faster than the other graph, but notice that it's like getting steeper and steeper and steeper, okay, in both directions. And so it's not quite the same. So there's something else going along with this rational function. And we're actually going to learn that this rational function has what's called an oblique or a slant asymptote. And we can actually find the line that it gets closer and closer to along this diagonal right here. And we'll do that in the next part of our lesson. Okay, so looking at that same example again, what do we know about the graph of this function? Well, we discovered that there was a vertical asymptote at x equals 1. We also determined the end behavior, that as x approached positive infinity, f of x approaches positive infinity, and as x approached negative infinity, f of x approached negative infinity. And all that was done in the previous example. Now there are a few other simple things that we can figure out. We could figure out the x and y intercepts. So at the y-intercepts, we look at when x is equal to 0. Let's do that next. And if we do that, we get 0 minus 0 plus 4 divided by negative 1, or f of 0 equals negative 4. And so we have a y-intercept at 0, negative 4. Pull that graph up, we can see that too. So there it is again. You see the y-intercept at 0, negative 4. We can also determine where the x-intercept is without needing to use this graph. So the x-intercept will be when f of x equals 0, or when 0 equals x squared minus 4x plus 4 over x minus 1. Okay, now in order for a fraction to be 0, the numerator must be 0. So we know that that answer is just when this is equal to 0, and that factors actually to x minus 2 squared. So our only answer here is x equals 2, and the x-intercept is at 2, 0. And sure enough, on our graph in Desmos here, you can see that 2, 0 is the x-intercept. So we know a few things about this graph. We know the vertical asymptote, we kind of know the end behavior, and we know the two intercepts. Those things don't give us a very good explanation as to why the graph looks the way it does. So the next step actually is, because the denominator has a greater degree than the numerator, we can actually rewrite this in a different form using polynomial long division. And that's exactly what we're going to do right now. We're going to take x minus 1 and we're going to divide it by x squared minus 4x. Sorry, we're going to take x squared minus 4x plus 4 and we're going to divide it by x minus 1 using our polynomial division. Let's just take a look at what we get when we do that. Okay, I'm going to do my best to do this on the screen here. So x goes into x squared, x times x minus 1 gives you x squared, take away x, and then we subtract. Negative 4x take away negative x is negative 3x. We get negative 3x plus 4. Okay, to get rid of the negative 3x, put minus 3 in here, and we get negative 3x plus 3. Subtract gives our remainder of 1. Now you might need to review some of the lessons we've already done on polynomial long division, but if you do, you'll remember that we can now rewrite f of x so that it looks like, okay, since it's x squared minus 4x plus 4 divided by x minus 1, it's equal to x minus 3, and I'm going to write the remainder of 1 as a fraction, plus 1 over x minus 1. So polynomial long division has allowed me to rewrite this rational expression here with this expression right here. It's kind of, I don't know, unsimplified if you want to think of it that way. I mean, normally you take this and put it together and make it into that. Instead of polynomial long division allows me to do the opposite. And the reason I'm doing that is that the equation in this form right here actually gives me a better idea as to what the graph looks like and why. So let's think about what happens as x gets very, very large, as x approaches positive or negative infinity. We can start with positive infinity for now. Notice that this stuff right here, as x approaches positive infinity, this fraction gets closer and closer to 0. And so what ends up happening is f of x starts to look more and more like the line y equals x minus 3, adding just a little bit. Now, if that little bit is positive, the graph's going to be above the line y equals x minus 3. And if that little bit is negative, then the graph will be below the line x minus 3. So we actually call x minus 3 a slant asymptote or an oblique asymptote. I'm going to use the word oblique asymptote. And that explains the sort of strange picture we got when we put it in Desmos. Let's just look at that now too. So if you look now, you'll see I've taken our graph. I've still got the vertical asymptote, but I've added the line y equals x minus 3. And you can see how our curve gets closer and closer to the diagonal line y equals x minus 3. Of course, y equals x minus 3 has a slope of 1 and a y-intercept of negative 3, since it's in y equals mx plus b form. And just like I said, sure enough, as x gets big, the graph is above that line. And as x gets small, the graph is below that line. So yes, the graph does approach positive and negative infinity, but it does so according to this slant or oblique asymptote, which it gets closer and closer to. There's one other thing that breaking up this function into its parts like this, sometimes we call this a sum of functions, a line plus this graph right here. Breaking it up like this also helps us determine what the shape of this graph must look like. So let's look at x minus 3. So we know that y equals x minus 3 is just a straight line. It has a slope of 1 and a y-intercept of negative 3. So there's a rough sketch of it. We actually know what 1 over x minus 1 looks like as well. It's very similar to the graph of 1 over x. It's just been shifted to the left, sorry, pardon me, to the right by 1, so it has a vertical asymptote at x equals 1. So there's a very quick sketch of 1 over x minus 1. Well, our function says take all the y values from this graph and add them to the values on this graph. So you can almost think of these graphs as being on top of each other, and you're adding them up to get their shape. Okay, what I've done now is I've taken the line y equals x minus 3 and I've graphed it again in red, and I've taken 1 over x minus 1 and I've graphed it in, sketched it in blue, but on the same set of axes this time. So remember that f of x is this plus this. So if we were to add the blue and the red, that should give us the shape of the graph. And we can actually use that idea to come up with what the shape of the graph looks like. Even though we've already looked at it in Desmos, it will explain why it has that shape, or it'll help to further explain it. Okay, so again, keeping in mind, these are simple graphs that we should know what they look like. So we add them together, starting from left to right. We're going to imagine adding the blue and the red sections together. Okay, so when we do that, starting at the left, notice we've got a big negative red, okay, plus a little bit of blue. And so our graph shape will be in here somewhere. Now, what ends up happening is that eventually the red gets closer and closer to 0, but the blue starts to take off towards negative infinity. So somewhere, this graph turns and changes direction like that. Now, if we look at our graph in Desmos, it sure looked like that as was at the point, at the y-intercept. We don't worry too much about where exactly that happens yet. That's more of a calculus question. Okay, remember there's the asymptote at x equals 1. So let's go to the left of the asymptote. Now we've got giant blue plus some negative red. And so the graph must do something like this right here. Okay, and as blue gets closer and closer to 0, eventually the red graph starts to take off. And so we're talking about adding these y values to these very small y values. And so if we did that, we get this right here. Now again, if we look at it in Desmos, you'll remember that this turning point happened to be exactly at the x-intercept. You can tell from looking, but don't worry about where that location is right now. So not only does breaking up, dividing using long division, not only does it help us identify this oblique asymptote, it actually kind of helps us determine what the shape of the graph must look like as well. So I know the shape of the graph not only from the oblique asymptote, but also from adding these two graphs together, I can kind of infer what the shape of the graph must look like. So adding these two functions together. Now that's a difficult concept. Even in class, students have trouble with this idea. So bear with me because we will do another example where we do it. And then the next lesson that I give you is just on adding functions. Sums of functions will further help you with this skill of adding two equations together. So let's move to our next example. Now I'm going to recommend actually that before we move on to the next example, that perhaps trying question 1 and 3 from the assigned homework problems would be helpful. Maybe watching that other video that I gave you would be helpful as well. Before we move on to this next problem that we're going to work on, it's a little bit more complicated, so I think that that's a really good idea that you take a look at question 1 here, okay, and this problem set right here. And the example I'm going to do is very similar to question 2 and quite a bit more difficult. So yeah, that's my advice before continuing. Okay, in this last example, I'm going to pretend I don't know what this graph looks like. Okay, so yes, we could plug that into Desmos and find out, but to make it more of a puzzle and make it more of a challenge, let's see if we can figure out what it must look like without using Desmos and see how close we are. Start with the easy stuff. There's a vertical asymptote at x equals 0 because of the denominator. Okay, since x can't be 0, it's impossible to have a y-intercept. However, g of x could equal to 0 so long as x to the power of 4 plus 1 equals 0. Oh, but that's not possible. So there's no intercepts at all. There's no x-intercept because y can't be 0, and there's no y-intercept since x can't be 0. As far as the end behavior goes, the degree of the numerator is greater than the denominator. So this thing blows up to infinity. And we should know that by now, just like the last example. And now the new thing we know is that when it blows up to infinity or negative infinity, when the degree of the numerator is greater than the denominator, and the last example we did long division to break it up, we can do the same thing here. However, since we're only dividing by a monomial, it's not necessary to do long division. You can actually just divide both of these terms by x squared and rewrite g of x that way. Let's see what that looks like. So taking x squared, dividing x to the power 4 by x squared gives you x squared, then dividing 1 by x squared gives you 1 over x squared. So we've written this as a sum of functions as well. Now let's think about what happens as x gets really, really big. As x gets really, really big, this portion of the graph, this becomes closer and closer to 0. So that's as x gets really, really big. Okay, I'm not going to leave that there because take that out. Okay, but that's what happens. And so what ends up happening is the graph looks more and more like x squared plus a little bit. And so that actually creates not an oblique asymptote, but what's called a parabolic asymptote. So there is what's called a parabolic asymptote at y equals x squared. So to just help you further understand that, imagine you have a number, even x equals 3. X equals 3, you'd have 3 squared, which is 9, plus 1 over 9. So you have 9 and 1/9. If x equals, say, 5, you'd have 25 plus 1 over 25, so 25 and 1/5. Well, that's very similar to the graph of y equals x squared. You just have that 1/9 or that 1/25 added to it. So we know that as this x values start to get bigger and bigger in this function, that this function will look more and more like the graph of x squared. In addition, we can also think about this as being a sum of functions. These are actually two very simple graphs, especially x squared. Let's just sketch both of them separately. So there's the graph of y equals x squared. Okay, it's a simple parabola. And then 1 over x squared is maybe one you are not quite as familiar with, but we did look at it in class. It's the reciprocal of x squared, and it's going to look like this. Okay, it has a vertical asymptote at x equals 0, and it curves up like this. It's always positive. It's an even function as well. So our graph is actually the combination of these two graphs added together. So let's take both of these and plot them on the same set of axes and see if we can figure out what the final graph will look like. Okay, so there you see them on the same set of axes. I actually just drew them freehand this time. So y equals 1 over x squared in red and y equals x squared in blue. Now I'm going to imagine that I'm adding these two functions together. What do I get? So I'm going to start left to right. And I'm going to start with where the blue starts. I mean, technically, the red is right here. The blue graph would be way off the screen there. And then same here, blue graph way off the screen. So I've got a positive big numbers. And I'm adding some smaller numbers. So the graph starts like this, above y equals x squared. Then eventually, the y equals x squared, the blue graph, the y values get small, but the red graph starts to take off. So eventually, it changes direction and does this right here. Okay? Now moving to the other side of the vertical asymptote. Okay, we've got big red plus a little bit of blue, means that the graph's going to look like this. And then for the same reason, eventually it changes direction like that. Big blue plus a little bit of red gives us this right here. So that's a basic shape. The black is basically the shape of g of x. One thing I notice now that we could have realized before too, is if you remember, if you look back at lesson 5.1, when we first started talking about rational functions, we not only do we sketch this graph, it will help you realize what the graph of 1 over x squared looks like, but we also talked about even and odd functions, not even and odd degree, but even or odd. This function is clearly even. It does not matter if you sub a positive or a negative value into either of these places, you'll get the same thing. Negative 2 to the power of 4 is 16, just like 2 to the power of 4. And negative 2 squared is 4, just like 2 squared is 4. And so sure enough, the right and left of the x-axis is the exact same picture. It's perfectly symmetrical. Now this is a jumbled mess, okay? We want to combine all the things on this page to get a good sketch. Okay, we know that this, not only did we use the blue and the red graph to get our final graph, but we also realized the blue graph is a parabolic asymptote, and we have a vertical asymptote at x equals 0. So if I'm going to sketch this whole thing right now and show you what that looks like. And there you see it. Okay, y equals x to the power of 4 plus 1 divided by x squared. As it turns out, sure looks like these points are at 1, 2, and negative 1, 2, but you do not need to worry about that fact right now. And if I were to add the parabolic asymptote, y equals x squared, you can see that the graph does start to look more and more like y equals x squared. In fact, it's almost like it's contained inside of y equals x squared. There we go. Okay, that's it for today. And like I said, this lesson's pretty challenging, a little bit long. The next lesson will help you understand some of these ideas, especially when it comes to adding functions together and what that looks like, that last step right here. Okay, the next lesson will help with that a bit. The CEMC website I gave you a link to also runs through examples, but it doesn't do ones like this with the parabolic asymptotes. It just does oblique asymptotes. Okay, let me know if you have any questions. Thanks.